Hi students, today I am going to explain about filters. I am Dr. B. RaviKumar, Associate Professor, Department of ECE. So far in previous lecture, we have talked about the rectifiers, how many types of rectifiers, half wave, full wave and bridge rectifier. Though we studied all rectifiers which converts AC input signal into pulsating DC output signal, but the output of the rectifier we can get only some percentage of DC output. So which contains both AC components and DC components. So that's why we need to pass through the other circuits which are called the filters. The output of a rectifier contains not only DC component and also AC components. So that's why we should go for filters. Filter is a simple electronic circuit which filtering out of the AC components which are coming from the rectified output. Generally, filters are used to minimize the undesirable AC components, that is ripple in the output, and leaving only the DC component which will be appear across the load resistor. The basic simple filter circuit, it is a filter circuit. Whenever we are giving the rectified output, let us take a full wave rectifier. Output is given to the input of the filter. The filter output, which may contains AC component and also DC components. That may be some kind of AC signal, and this is the DC components. So when we use filters, we can reduce some kind of AC components which are existed in the rectified output. So we have different kinds of rectifiers based on the some of the elements which are used in the filter. The elements are inductor, capacitor, resistor, and combination of these elements. When we use those elements in the filter, which can filter out of the AC component which are present in the rectified output. So these are the basic filters: inductor filter, capacitor filter, and both combination of L and C, LC filter or L section filter, and the CLC filter or pipe filter. Let us see one by one. Inductor filter. What is an inductor filter? When we use an inductor which is connected between rectified output and a load resistor, a huge number of or high inducting values is connected between rectifier and load resistor. Inductor filter is also called choke filter, and the inductor which is connected between rectifier and the load, when it is connected between rectifier and the load, then because of the property of the inducting material which can access DC component and blocks the AC component. The filter action of an inductor filter, as I said, which depends on the property of an inductor. What is the property of an inductor? The property of an inductor which opposes any change in the current flow through it, and which allows a constant current flowing through it. Whenever it is opposed any change in the current flowing through it, which is similar to the AC current or changing current which is coming from the rectified output, and which allows the DC current means the DC current which is coming from the rectified output. Inductor filter which offers high resistance to AC component and no resistance to DC component. Whenever it offers high resistance to AC component, just like this is the rectified output. In this rectified output, we have AC component plus DC component. So whatever the AC component coming from the rectified output, due to offer of its high resistance for the AC component, it stops the AC component and which allows DC components. This is the circuit diagram for inductor filter. So we can use this inductor filter here between rectifier and load resistor. Here this is the maximum voltage VL max, and this is the output for rectifier. Let us take a full wave or bridge rectifier. The blue color line which represents small ripples which are available still in the filter. So this output with the choke filter or L filter, this is the without filter. Whenever this filter with a inductor, the output consists of both the DC component which is represented by dotted lines and the AC component which is represented by a small ripples. So that DC component is approximately is equal to 2 Vm by pi, and in the rectified output now it is improved in the filter output. So here by using the inductor filter we can reduce the ripple factor. The output of the inductor filter should consist of only DC voltage, but in practice, in a real-time practical circuits, it contains also a small AC component and along with the DC components. The ripple factor of an inductor filter for 50 Hz of the AC input signal is given by gamma is equal to RL by 3 root 2 into omega into L, where RL is equal to load resistor and W is equal to frequency in radians and L is equal to inductor value in Henry, and which is approximately equal by substituting a constant 3 root 2 into 2 pi into F is equal to 50 Hz. Then we will get RL by 1330 into L value. With this equation will help in the problems. They have given inductance value and load resistor value. What will be the ripple factor? When we see this diagram, the ripple factor will decrease as load resistor is decreased, and the ripple factor will decrease as L is increased. So it is directly proportional to ripple factor is directly proportional to load resistor RL and indirectly proportional to inductance value. Suppose when we prefer different loads, so in all cases this inductor filter is not at all useful. It is useful for and it is effectively used for heavy load current, and when that means that is heavy load current, which means less resistance, less load resistance. For less load resistance, the ripple factor will be less, and this kind of loads we can use the inductor filter. When we use light loads, that means large resistance, when heavy resistance, then it is directly proportional to ripple factor, so that it will not at all useful for filter action. So when ripple factor is, again it will almost equal to, without filter we can use only rectifiers, then the efforts, then the use of this inductor filter would be wasted. So that's why the effective of this inductor filter for heavy load current or the load resistor is very less. In that case only, then this ripple factor will be very less. And also, if suppose in the denominator when we observe, it is indirectly proportional to inductor. So when we use in a high inductance value, when we use inductor value will be very high. When the inductance value will be very high, our ripple factor gets reduced. But problem was that when a large inductance, which gives a large inductance means, so which effect on the DC load voltage appear across the load. So when DC voltage decreases, when the large inductance will be available, and the DC voltage drop will be less, then again the purpose of this filter would be wasted. Next, we'll move to the capacitor filter. What is the capacitor filter? When we use the element capacitor, which is connected between rectifier and a load resistor, then the circuit can be used as the circuit said to be capacitor filter. Again here, how can we use, or how can we got this capacitor to have used as a filter when we connected in parallel with the rectifier and a load resistor? So here also capacitor. So we have already know that the property of capacitor. Based on the property of capacitor, we can use the capacitor is used as a filter circuit in the rectified output. What is the property of capacitor? The capacitor, just like, is opposite to inductor filter. So before going to the operation of this capacitor filter, why we choose, already we have an inductor filter, again why we go for capacitor filter. In the previous figure, inductor filter, an inductor filter is suitable for only heavy loads. That means a load with a smaller value of resistance. And this inexpensive filtering action for these heavy loads, so we can go for some other filter which is called capacitor filter. The inexpensive filter for light load is available in the form of capacitor filter. Here the load resistor will be high, then we can use for capacitor filter. It should be remembered that capacitor filter, the capacitor value always connected in parallel with the load resistor and the rectified output. What is the purpose when we connecting load resistor in parallel? When we connected in parallel, we have known that the property of capacitor which oppose the changing voltage and allows the changing current. And simply we can say that the capacitor blocks DC and which allows AC components. How can we use when capacitor allows AC component and which blocks the DC component, so the rectified output, full wave rectified output, which consists of AC component plus DC component. All the time when I am saying a wave, by seeing the waveform which consists of AC component plus DC component, means when we mathematically derive the equation for this rectified output according to Fourier analysis, it has DC component. For example, it is a full wave rectifier 2Vm by pi. It is a DC component plus AC component in terms of sine omega t. But I am not mentioning all the frequencies and amplitude. So omega t plus sine, based on the rectifier output, it has even harmonics or hard harmonics. So this is the AC component, entire things. So it has first harmonic, second harmonic, third harmonic. So when we expanded in the Fourier series, it consists of DC component and all AC harmonics. So that's why I'm saying rectified output also having AC component and DC component. So this kind of AC component and DC component passing through the capacitor, and passing through the capacitor, which blocks DC and allows voltage. Generally, capacitor start to charge voltage, start to charge and store voltage. So whenever this AC voltage and DC voltage appear across the capacitor, whatever the AC component, the AC current flow allows the capacitor and which is connected to ground, all AC components or AC current flowing through the capacitor connected to ground, and nothing will be left across the capacitor of AC component. At the same time, which blocks the DC component, which means whatever the capacitor stores the DC value, so the voltage across the capacitor is VDC only. When we get this DC component across the capacitor, similarly, when we connecting the load resistor across in parallel with the capacitor, whatever the voltage dropped or voltage stopped across the capacitor, that will same voltage will be appear across parallel connection of load resistor. So parallelly, in parallel, voltage is same, in series current is same. When same voltage appear across the load resistor, so we will get the DC voltage appear across the load. So AC component going through the ground and DC component stop across this plus and negative polarities of the capacitor, that voltage, same voltage remains appear across the load resistor. So this way, in capacitor filter, we can get the DC component, we can filter out the AC component, and we will do the reduce of this ripple factor in the capacitor filter also. But capacitor filter, how this capacitor filter voltage VDC stores in the capacitor can be explained, can be understood from the waveforms. The waveform of the rectified output, waveform of the voltage across capacitor, and the waveform of the load resistor. So let us see, by seeing the waveform, we can try to understand that the capacitor filter output. Here, if you see, during the positive half cycle of the AC input signal, during the positive half cycle of the AC input signal, we know that filter rectifier and then connected to filter. So in the positive half cycle diode, if we consider the full wave rectifier diode, D1 is conducting and diode D2 is non-conducting. So when we see this diagram, for example, this is the one it has three different kinds of filters with rectifier with the filter. This one is the half wave rectifier with the filter. This one is the full wave rectifier by connecting capacitor across the load in parallel with load, full wave rectifier, bridge rectifier. This one is the full wave rectifier. So the load capacitance, capacitor across the load. So here, similarly, when we see this during positive half cycle for full wave or bridge rectifier. So which full wave rectifier which start conducting, and you will get the rectified output as shown in the figure, dotted line. If it is half wave rectifier, you will get a one cycle with a suppressed during negative cycle pi to 2 pi. If it is full wave rectifier, you will get the full wave rectifier output. So if in this case, during positive half cycle of the AC input voltage, diode is forward bias in the half wave rectifier, which it allows the capacitor to quickly charge its maximum value. Why? Because if you see here, this positive half cycle, diode D1D is conducting. When diode D is short circuit, immediately whatever the voltage, it gets started to charge. Okay, 1 volt, 2 volt, 3 volt, 4 volt. So it's maximum. This is the maximum value. So at maximum value, the capacitor start to charge. When capacitor start to charge to the maximum voltage, by seeing this diagram, so when we see this start to charge, so the voltage available in the across the capacitor. What happens when just the input voltage, if you see this case, because we are assumed that our case is half wave rectifier, so this dotted line represents the half wave rectified output that can be passing through the capacitor. Then up to this point to maximum voltage, it will get charged. So when immediately the rectified output, the waveform reduced to maximum value, below that maximum voltage. When below that maximum voltage, what happened? The diode gets reverse biased. When the diode gets reverse biased, in the figure, diode gets reverse bias. So when the diode gets reverse bias, this is open circuit. When it is reverse bias, open circuit. When it is open circuit, there will be no connecting path to charge again, but it will connected to load resistor. The property of capacitor, when it has fully charged and it stores some energy or stores some voltage, whenever it is low conducting path or resistor connected across the load, immediately the capacitor have a tendency to discharge that energy, they discharge that voltage through a low resistance path or load resistor. So here, up to positive voltage, maximum voltage, it will charge to Vm. When it is input voltage or rectified output voltage just below the Vm value, then it will disconnect, diode disconnect, and capacitor is connected to load resistor. When it is capacitor connected to load resistor, again, so it will start to discharge. This can be shown in the figure. So whenever dotted line of this waveform below this maximum voltage, until it's reached to a significant voltage for PN junction diode gets forward bias, this will be discharged. This will be discharged. Again, when it's reached to the input voltage gets forward bias of this PN junction diode, this again gets to charging. This is for half wave rectifier with the filter, capacitor filter. When we see the full wave rectifier, here when full wave rectifier, the voltage start to charge up to maximum voltage Vm. When it is full wave rectified output gets below this maximum voltage until the rectified output reach to next to the voltage level, which is gets forward bias to PN junction diode, it will be recharged. Discharge, again charging, discharging, charging, discharging. This charging and discharging of the waveform of the rectified or filter output will be mathematically approximated to this kind of triangle waveform. When we compare with this dotted line rectified output, this ripple or this waveform of the capacitor filter having a less AC component and less ripples compared with the rectified output. It is important to note that because of diode has a less resistance, ideally zero forward bias resistance. Whenever diode has zero forward bias resistance, so here when zero forward bias resistance, If it is zero forward bias resistance, so immediately without takes much time, immediately capacitor start to charge. So that can be shown in the figure. The time period for this charging time is very less, ideally zero, but practically a small resistance exists in the forward bias PN junction diode. That resistance multiplied with the capacitance is nothing but time constant for charging. So tau is equal to C into RF, forward resistance of the diode. So when we take this time period, T1 is equal to, or tau 1 is equal to, it is nothing but the resistance of the diode RF into capacitor. This much of time takes to get charged. So within short time, the capacitor start to charge and reach to maximum voltage. But whereas in this discharging path, so when below Vm, until wave is until the wave is reached to zero and a negative voltage, and again come back to positive voltage, which is about to cut voltage of the PN junction diode, then it gets discharged. But the time taken for this discharge is very large, because whenever this period diode gets reverse bias, so which resistance is connected for the capacitor? Load resistance. So when the load is always compared with the forward biasing of the diode, this load resistance is very large. When the large resistance and multiplied by capacitor, the time constant to takes of discharging path or discharging of this capacitor voltage is very large. So in this case, when the capacitor discharging through a load resistor is very large, that means the maintaining of this voltage slowly discharging through a load resistor means we can store we can get the DC voltage across the load for a long period. So that can be useful for load by the load. So when we use this kind of assumption of the load resistor or for the large load resistor, then we can get the large time constant to get discharge. That can be used by load. So this way, it is also mentioned that the time constant for discharging path or discharging period is 100 times greater than the charging time period, so that we can get this DC output voltage getting to load is very large. So the time constant should be large enough. So the overall output for this waveform is this kind of waveform we can see here. What is the ripple factor for a capacitor filter for a 50 Hz and 230 volts approximately of AC input signal, which is given by gamma is equal to 1 by 4 root 3 F into C into RL. This is actually derived from the capacitor filter. So here I am directly giving to the formula for ripple factor. So actually the derivation takes from the capacitor filter for how much time the time for charging period and the time for discharging period is 100 times greater than the T1. When we take how much, if though the time period is different for charging and discharging, but the charge stored in the capacitor will be the same in the same charge discharge with the T2 time period. So that's why when we equating Q1 is equal to Q2 or QT1, QT2, whatever the charge in a span of time, how much charging value, how much voltage charge through capacitor, the same charge discharging slowly in the T2 time, but Q is same, charge is same. So how to get the charge? By forward resistance of the diode and the capacitor. So we can take the relation between current and time. So Q is equal to charge, Q is equal to IT, and how to discharge of the capacitor through load resistor. So we can take the load resistance here. So the charge of the charging through load resistor. When we equating QT1 and QT2, we will get the ripple factor. So we will get the equation for the AC component and DC component current. So then we can substitute the ripple factor. So then we will get 1 by 4 root 3 F into C into RL. So I am directly giving the equation for the ripple factor for capacitor filter. Gamma is equal to 1 by 4 root 3 F into C into RL, where F is the frequency of the signal, rectified signal or input signal, and C is the capacitor filter for capacitor, RL is the load resistor. When we substitute this constant value 1 by 4 root 3 and F is 50 hertz, then you will get 2890 divided by C into RL. In the problems, they have given capacitor value and load resistor. Directly we can find out 2890 divided by C into RL. Okay, what will be the relation between the ripple factor and load resistor and capacitor? If you see here, gamma is inversely proportional to the load resistor and inversely proportional to the capacitor. So for large loads, heavy loads or large loads, load resistor is very large. Load resistor is very large. So when RL is large, then you will achieve the less ripple factor. So capacitor filter, because of this relation, this can be useful for large resistance or light load current. So heavy load resistors we can use, we can prefer for capacitor filter. And also if we can increasing the capacitor value, a large capacitance when decreasing the ripple factor. When we compare with the inductance, increasing the inductance which occupy larger space, but increasing the capacitance will occupy very less space. So it's better to increase capacitors under capacitor so that we can reduce the ripple factor for the heavy load circuits. This is about capacitor filter. So we can prefer for large loads, and even though we can increase the capacitor, no problem with the ripple factor. We can see reduction in the ripple factor. Next filter is called LC filter. As we studied, inducting filters which allows the DC component which blocks AC component, and whatever the allows DC component flowing through the load resistor will get the DC output voltage. And in the capacitor filter, because of its property which blocks DC component and allows AC component that can be connected to ground and AC voltage available across the load. But the ripple factor for this inductor filter, which is directly proportional to the load resistance, and the same ripple factor which is inversely proportional to the load resistor RL in the capacitor filter. So can we use both the inductor and capacitor so that we can independent of load resistor? Yes, it's true. So when we combining the inductor filter and capacitor filter, as shown in the figure, first connected an inductor in series with the rectified output and load resistor, and I take the capacitor in parallel with this in between the inductor and load resistor. Then we can say that LC filter. When we use this combination of inductor and capacitor filter in the filter circuits, then the ripple factor will get almost independent of load resistor. The ripple factor of an inductor filter, gamma, is equal to root 2 divided by 12 omega square into L into C. So there will be no RL term. That means it independence of load resistor. We can use any kind of load resistor when we use combination of L and C filters. So root 2 divided by 12 omega square L into C, which is equal to 1.195 divided by LC by considering all the parameters 12 root 2 by 12 into 2 pi into F. F is equal to 50 Hz. By substituting all the parameters, we will get 1.195 divided by LC. So when see the waveform also by using this L and C, so we can take the filter for full wave rectified output, but we can achieve a small ripples compared with the previous L and C filters. But important thing is which will be useful for any loads independent of load resistor. Now the last filter, which is called CLC filter. The CLC filter also called pi filter. The Greek symbol pi. Why it is called pi means if you see the diagram, the pi CLC filter. So we can use two different capacitors C1 and C2 and one inductor L. When we take this capacitor first, the rectified output is given and passing through the capacitor first, and then the current passing through the inductor, and whatever again passing through the capacitor. So when we connecting this C, L, C like a pi symbol pi, then that's why it is called pi filter. When we connecting this way, so we can reduce the ripple factor compared with the previous one. So first we will passing through the capacitor and then passing through the inductor and then passing through the again capacitor. So when we passing through first initial passing through the C1 capacitor, which blocks the DC component, allow the AC component. So whatever the AC component connected to ground and only DC component will be available. That DC is flowing through the inductor. That flowing through the inductor because which allows DC and blocks AC component. So which allows DC component, that DC is passing through the output of the inductor. So again, whatever the output coming from the inductor filter, again passing through the capacitor. So we can get more DC component across the inductor capacitor, which will be parallelly connected to load resistor. The same or DC output will get across the load resistor. So here we need to remember that the first capacitor already blocks the AC component, allows the AC component and which filter and captured the DC component. But then why we connecting again CL and C means, so C capacitor alone cannot get the perfectly DC or pure DC. So it has also small ripples. That ripples can be measured by the equation of gamma in the capacitor filter. So again, the output of the capacitor filter having a small ripples and a large DC. This can be filtered out in the L filter. Again, still this L filter again, it has small AC and that DC that can be passing through the C2. Then you will get the or almost negligible AC component and you will get DC component. Under this CLC filter, it is required for low output current and high DC output voltage. And then ripple factor for an inductor filter for this is given by gamma is equal to 1 divided by 4 root 2 omega over 3 C1 C2 L into RL. We have C1 C2 2 capacitors and 1 inductors. So when substituting all the constant parameters 4 root 2 2 pi f whole cube, and then we achieve 5700 divided by C1 C2 L into RL. So this kind of formula which can be helpful for finding ripple factor for CLC filter. So and also in the problems they have given ripple factor. So in order to get that much of ripple, like 1% of ripple, and given parameters C1 and C2, what will be the RL? And by giving the ripple factor and C1 C2 and RL, what will be the inductor value suitable choosing of this inductance value to get that much of 1% ripple factor. So that's why we can get this formula to get the designing of inductor or designing of C1 and C2 for the given parameters. So these all filters, L filter, C filter, CLC filter, LC filter. Simply these kind of LC resistor elements are used in the filter. So when we use this filter, the rectified output connected to filter, and then this filter when giving to rectified output, and you will get small ripples in the rectifier in the filter. So we can achieve our target almost negligible AC component. So then whatever the small variations we cannot filter out in the filters, then given to regulators. In this regulator, sometimes old basic regulators like a Geno diode connected across this filter, then it will be filtered out or smoothing this AC component to constant DC component. Our advanced circuits of ICs, regulator ICs, we can passing through this filter, output passing through the regulator, we can smooth out and gets perfect DC in the output. That's why the output immediate of this rectifier will give to the filter, and still filter having these components, both AC and DC components. So again when we connect it to regulator, then which will filter out and will get perfect DC. Okay, so this is the filters, different kinds of filters which will be used in the power supply block, power supply mode. So the circuit which represents the filter is very simple because of its like elements which are used in the filters like inductor, capacitor and combination of those. So based on their property, we can use in the electronic circuits of this L filter, C filter and the LC filter, CLC filters, so that we can get the perfect DC. Well, most probably we can avoid the here like a large amount, like heavy load inductance when they compare with the large capacitance. So as much as time as much possible, this capacitance is value is very large and the inductance value is very less. So this is all about the filters. So now when I recollect that a power supply block, transformer, rectifier, filter and regulator. So the purpose of our block diagram will be completely fulfilled by passing through this pure AC signal, to like a transformer and a rectifier, and then passing through the filter, and connected to regulator, like a Geno diode and connected to load resistor. So these are the rectifier, this is filter, this is regulator, then connected to load. Then we can achieve pure DC. This is what we expect. 230 volts, 550 Hz AC and a required voltage 5 volt, for example 5 volt for mobile phone. So you will get a pure DC by studying all these like a transformer, rectifiers, filters and then regulator. So up to now we have studied about this rectifier and the filters. So in this way we can get the AC signal which will be converted into pure DC signal by passing through these blocks. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.